This is a presentation on system dynamics and control inverted pendulum abstract. This is the final presentation. In the final presentation, we're just going to focus on the MATLAB evaluation part of the project. As a recap of the project, we wanted to set up a controller, design a controller for an inverted pendulum. And an inverted pendulum is a very common system that we study in system dynamics and controls. There's many applications for the system, such as spaceships, or before they are launched, they are treated like an inverted pendulum. And the whole point of this is to design a controller system that will keep the inverted pendulum balanced. The first slide goes through the project criteria. Here we have the free body diagram. We derive the equation of motion, establish the constraints, and derive our transfer functions. This is another schematics of an inverted pendulum, and our specific criteria would be to have the pendulum return to its initial position in 5 seconds or less, have the pendulum angle could not exceed more than 20 degrees from the initial position, and set the equilibrium position for the inverted pendulum at theta equals pi, which is standing straight up. When we model the equation for the system, we have 2 equations. One is the motion of the cart. It's a linear equation, where the other one represents the motion of the pendulum, which is an angular nonlinear equation. To be able to establish a transfer function, we'll need to go through a series of steps to linearize the pendulum equation. Once we achieve that, we get this equation, and we can now derive the transfer function for the system. In this particular slide, we have now derived the transfer function for both the pendulum and the cart. And this transfer function will help us understand how the input, which is the external force acting on the cart, is affecting the cart's motion and the pendulum. And then we will now go into state space equation, which is specifically, it's going to help us set up the matrices by assigning variables to each aspect of this equation. The matrices would also help us when we go to MATLAB to input these equations and run simulations to see the behavior of the system. Here's our state space equation. It's important to linearize the system because we couldn't run simulations with a nonlinear system. And we'll also have to go back when we actually do the simulations to build a nonlinear system to be able to test our simulations. As we go into the MATLAB representation, continuing, we're picking a mass of the cart at 0.5 kilogram, the mass of the pendulum at 0.2 kilogram, the coefficient of friction for the cart at 0.1 Newton meter per second. The length of the pendulum to the center mass is 0.3 meters. Mass moment of inertia of the pendulum is 0.006 kilogram times meter squared. And then F represents the force applied to the cart, X represents the cart position, K is a spring constant, and C is viscous damping constant. For the first part of the project, we're not going to consider spring or damper effects. We're only going to look at the equation of motion without those effects. And then we'll compare them to see when we add those effects, how does it change the system. Okay, in the MATLAB code, we're able to establish a transfer function, and this is going to be in the Laplace domain, which is a continuous time transfer function. If we design the controller as an open loop system, it wouldn't meet the necessary criteria of our design. So this graph represents an open loop impulse response system. And as you can see, the displacement of the cart and the displacement of the pendulum goes on infinitely. But as we continue to adjust our system to a more closed loop system, we're able to achieve the desired motion as this graph illustrates. The car position starts at 0 and it goes in the negative direction to closer to -5. The negative direction is about 5 meters. Then it stays at that distance. Whereas the pendulum starts at 0 radians, it goes to some oscillation, and then it comes and returns back to its original, all within 5 seconds, meeting the criteria of the design. Then we get into controllability and observability of the system. This is where we see how the controller and how effective the controller is working on the system. And this does validate, and having these flows, it validates that our system is in fact controllable because we're working in a 4x4 matrix. And then we get to the point we're going to add the effects of a spring and a damper. In the first part of this presentation, we're just looking at adding the effects of the spring without a damper. We can see that it does create some sort of disturbance in the system initially. Once we adjust our matrices, we're able to achieve the same result as when we didn't have neither the spring nor the damper. But something different happens when we take away the spring and add the damper. It creates a larger disorder in the system, and it makes it harder, even after we adjust our matrices, to achieve the desired output, as this graph illustrates. The next part we're going to skip to is the actual simulation part. But before we get to that, it's worth noting that when we add both the spring and the damper at the same time, it causes even a greater, initially causes even a greater disparity in the system. But as we adjust, we can see that the system starts to head towards a more satisfactory pattern. Eventually, we will be able to achieve the desired output, but we will need to do a lot more adjustment to the controller design. And here, this is when we optimize the system. First, we establish our equations. This is the equation of motion for the acceleration of the car. This is the acceleration of the pendulum. These are the external forces working on them, and N is the normal force of the pendulum acting on the car. First, we have to set up our system. Then from there, we go in and set up our subsystems, where each of these blocks represent each of those equations that are listed above. And when we apply the force to the system, we use a series of integrals and different components to see what position and angle we're going to get out of the system from this one applied force. And this is a schematics of the system where the pendulum is suspended slightly above the cart. And here's our graph. This represents the displacement of the cart, where this represents the displacement of the pendulum. And as we can see, we have a period that usually takes about, we're able to get back to our original point every 2 seconds. So it continues to oscillate, but as we get further out into 20 seconds, the oscillation gets more rapidly, making the system harder to remain stable. And that will conclude my final project. Thank you very much.